Just one.
Two things we're doing the next talk is for the speakers that are coming up, we're going to, just like we just did, we're going to close your laptop and hand it to you while you're answering questions. That's not a sign for you to get off. It's just a sign for us to set up the next speaker so things are a little more seamless. And I just want to say you were so good at asking questions. You stood up, you were loud, it was great. Nicely done. If other people follow your example, all right. So the next speaker is Farzad Ehtemam with Tom Vanderbogen as a collaborator, and let's just talk.
All right. Okay. How many people here have heard of David Winter's dataset? Probably a lot of people. So I think that's kind of terrible. I don't know why, but for the last 30 years, the biomechanics and motor control community has done really poorly in sharing some really good data sets. And I know that there are lots of other fields that they are hugely benefiting from having some really good data sets that they can test models on it, they can test different questions on it. So we recently collected some data. I'm going to introduce the data set, and then I'm going to talk a little bit about some exploratory data analysis that we are doing on the data. So we apply mechanical perturbations of the treadmill. This is how one of the trials look like. So as you're walking on a treadmill, you are facing with different perturbations. So we can perturb the belt, so the speed of the belt. So it's going to be anterior-posterior perturbation. And we can also have lateral perturbations of the treadmill, or we can have mix of both of these two. So this is how the data set looks like. So we applied continuous pseudo-random perturbations. And the first set of experiments applied anterior-posterior perturbation. So this is perturbing velocity of the belt. We had 2 different amplitudes of perturbation and 4 trials per amplitude, and each trial is about 4 minutes. Then there was another set of experiments that we applied a mix of anterior-posterior and mediolateral perturbation. And we applied that at 3 different speeds. And we measured kinematics and GRFs and EMG. And in total, we had 21 subjects, and this data set has over 50,000 gait cycles. So this is how some of the kinematics looks like. So this is joint angles. We were looking at how the speed of the treadmill is going to affect how you respond to perturbation. So there's this thing that we always do is that we average over all gait cycles. You can see different speeds here, slow, normal, and fast. That is 0.8, 1.2, and 1.6 meters per second. And as you can see that they're pretty similar. Sometimes you see some differences, like the fast walking, the ankle shows like some difference, for example, if you compare it with the slow walking. But for most parts, if you just look at the average data for perturbation, you cannot see the effect of perturbation. So what we were interested next is that if the perturbation has any effect at different speed on the coordination between lower extremity. And one of the things that people do is that they look at planar covariation of elevation angles for the thigh, for the shank, and for the foot. So what that means is that if you draw the 3 elevation angles in the 3-dimensional space, you can, under many different conditions, you can basically fit a plane to your data. So that's going to be your gait cycle, and it has been shown that basically 2 components pretty well can explain the data. And they have shown that pretty much it's the work of Ivanenko group about like more than 10 years ago. They have shown that for many different conditions at different speeds, this correlation exists. But they also have shown that some conditions, like for example, if you start walking on a slippery surface, this relationship can be broken. So our question was that, does the perturbation basically break this correlation or not? And the way that people analyze this covariation is they basically use PCA. And most of the time, 2 components can explain most of the variability in the data. So what I have here is the responses to perturbations. And it's slow, normal, and fast walking. So if you draw the elevation angles, you can see that more than 99% of the variability in the data during perturbation is explained by only 2 components. Which means that even during the perturbation, subjects were pretty good to hold that relationship. Now, the next thing that we looked at was the stride time variability. So we looked at coefficient of variation. That's one of the things that people look to see that how much is the variability in each trial. The problem with that is that it's actually a good simple measure, but the problem is that it reduces the entire trial to just 1 mean value and 1 standard deviation. So it doesn't provide you with much knowledge, but it's just a good first measure to look at. The next thing that we looked at long-range correlations. We used determinate fluctuation analysis. And what determinate fluctuation analysis does basically is that it basically chops your data to different window sizes. And for each window, you're going to fit a model, usually a linear model. And then you are going to see that how good basically the model can explain that data in that window. And then you're going to see that what is the effect of window size on that basically correlation. And it has been shown that if the data is close to a totally random process, like white noise, you can see that there is no correlation between the stride that you have right now versus like a stride in the past. But for gate data, they have shown that there's some good correlation between your current stride time and the past stride times. So this is a measure to basically tell you that if basically you are using the information in the past or not. And the way that people calculate this is that they calculate a scaling exponent. And they have shown that for white noise, the scaling exponent is 0.5. For brown noise, it's 1.5. So for different processes, we know what the scaling exponent that explains the fluctuations, what that exponent is. Now so for normal walking, people have seen that how the speed affects this correlation. But for perturbation, we didn't know how this affects the correlation. And for fast walking, we observed that the correlation explained fast walking as if it was white noise, meaning that people do not use much of previous information in their stride times. So this was pretty interesting to us. We still don't know why this is happening, but we are basically working more on this to understand that what happens during fast walking when you apply perturbation, that people do not rely much on the previous information from the previous strides.
Okay. So we have to stop there for questions.
Yeah.
So we have time for one question. So does anybody have a question?
Hello. Okay. Do you see that these behaviors are the same for just the AP perturbations or the AP and medial lateral perturbations combined?
We haven't done that comparison yet, so this is an ongoing project. So what we have done for this part is we have looked at the mix of medial lateral and anteroposterior perturbation. So the next step is to see that how does the anteroposterior alone compares to the medial lateral perturbation. So this is ongoing research. But so far we have seen that for the mix of anteroposterior and medial lateral, the way that they behave for fast walking under perturbation, they are not using much of the information that they had from the past strides.
Where do people find this data set?
So we're going to publish it soon. So look for it. We're working on the data paper. So we're hoping that it's going to come out before the end of the year, hopefully.
Okay, great.
Yeah.
Thank you very much. Let's thank Farzad.
I just want to remark that there is an earlier version of a data paper from the same lab, which is also really good.
Yeah, the problem with that data set was that it's just raw data, so it's hard for some people to use it, but we're going to publish both raw data and